Okay, let's discuss this practice exam, the third practice exam. First one is about the composition. So we have fx, square root of x, g of x, 2x minus 1, h of x, x squared. Okay. Okay, good. Now we're going to find the value of each expression. A, f compose g evaluated at 5. By definition, this means you're going to evaluate g at 5 and then evaluate f at g of 5. G of 5, so 2x minus 1. 2 times 5 minus 1 is 9. So this is 2 times 5 minus 1 is 9, sorry, 9, not g, 9. Okay, then f of 9, square root of 9 is 3. This is square root of 9. This is number 9, not g, not q, number 9. Okay, so the first value is 3. B, what is B? B is h compose g compose f of 9. Okay, so it means you're going to evaluate f at 9 and then g at f of 9, h at g of f of 9. So we're going to peel the onion. So we keep the h and g, f of 9. F of 9, we just know that f of 9 is 3. So this is g of 3. G of 3, 2 times 3 is 6. 6 minus 1 is 5. So it's h of 5. Then h is x squared. 5 squared, 25. Okay, this is our first evaluation problem. Okay. And second, we have fx equal to 1 over x plus 2, gx equal to 4 over x minus 1. Then we're going to find the composition of a function. So a, f compose g. F compose g. When we try to find the expression, we of course place x here. So this is f of g of x. G of x. Okay, that's right. This step. G of x is a 4 over x minus 1. And then you're going to apply this to the f. So x is here, so it's a 1 over whatever inside 4 over x minus 1 and plus 2. Okay, so let's check. We multiply top and bottom by x minus 1. So it's x minus 1 on the top, x minus 1 on bottom. This x minus 1 cancel, you get 4 and 2 times x minus 1. Okay, so it's x minus 1. Here's 2x and plus 2. See, it's 2x minus 2. Minus plus 4 is plus 2. So this is a f compose g. What is the domain? The first, if g makes sense, so x is not equal to 1. And the final thing does make sense, so the x is not equal to negative 1. You see here, when x is negative 1, this denominator is 0. So the domain is a set of all x. X is not 1, x is not negative 1. Okay, x is not 1, x is not negative 1. The expression is like this. Is a domain. So the domain should make the original function reasonable, also make the final function reasonable. Second part, g compose f. G compose f of x is a g of f of x. Fx, what is fx? Fx is 1 over x plus 2. G is here, so it's 4 over 1 over x plus 2 and minus 1. And we simplify it, we multiply top and bottom by x plus 2. So we get 4x plus 2, 1 minus x plus 2. So this is a 4x plus 8 over negative x minus 1. Minus 2 plus 1 is minus 1. Okay? So what is the domain? Domain first, x cannot be negative 2. And second, this denominator should not be 0. So x cannot be negative 1. This is the domain. Okay? X cannot be negative 2. It comes from g of x. Where's g of x? X cannot be negative 1 comes from this final function. Okay, this is our second problem. Third problem. Find the inverse of the function. Find the inverse of this function. Okay, what is the inverse? So first you let y be square root of x plus 2 minus 3. You're going to solve x in terms of y. So move 3 to the right, left side. And then we square two sides. And then we move 2 to the other side. So this is a plus, my bad. After that, you exchange x and y. And this is the inverse function. This is an inverse function. Okay? The domain of the inverse function. See here. This whole thing is at least 0. 0 minus 3 is negative 3. So it's at least negative 3 to infinity. It can be as large as possible. At least 0. 0 minus 3 is negative. So this is the domain. This is the expression. Okay? Problem 4. We have function f defined by this set of pairs. Negative 1, 5, 0, 0, and 2, 6. We're looking for f inverse of 5, f inverse compose f of 2. Okay, we're looking for those. F inverse, what is f inverse? You just exchange those two numbers. So negative 1, 5, you write it 5, negative 1. 0, 0 is 0, 0. 2, 6 becomes 6, 2. This is f inverse. You exchange input and output, you get f inverse. And then f inverse of 5, you check. When you have 5, the corresponding number is negative 1. So f inverse 5 is negative 1. F inverse of f of 2. This one is undefined. It is defined, sorry. It is equal, see here, f of 2, by definition, f of 2 is 6. F inverse of 6 is 2. F inverse of 6 is 2. This is exactly the cancellation. You cancel f inverse with f, you get 2. And you have to make sure this 2 is in the domain. If 2 is not in the domain, this is undefined. If 2 is in the domain, you just directly cancel the f inverse with f, you get 2. Okay? 5. So here, f inverse compose f is identity function. In other words, let's write the other words. If x is in the domain of f. If x is in the domain of f, f inverse compose f of x is equal to x. Okay, number 5, find the vertex and the symmetric axis of the graph. Find the vertex and the symmetric axis of the graph. Okay, so first let's recall what is the formula. Ax squared plus bx plus c. What is the vertex? The vertex is x is equal to negative b over 2a. I'm sorry, not the vertex. The vertex is a negative b over 2a and 4ac minus b squared over 4a over 4a. Yes, this is our vertex. The symmetric axis is x equal to negative b over 2a. So let's just plug in. So the vertex is negative, b is negative 4, 2a is 2 times negative 2. Be careful, a, b, c contain the sign. And 4ac, 4a is negative 2, c is 3, minus negative 4 squared. Wow, it's bad. 4a, 4 times negative 2. Okay, let's continue. Negative 4 over 2 times negative 2 is negative 4. Negative 4 over negative 4 is 1. So it's negative 1. Here is 4 times negative 2 is negative 8 times 3. Negative 24 minus negative 4 squared is 16. 4 times negative 2, negative 8. So it's negative 1. This is a negative 40 over negative 8 is 5. Okay, so vertex is negative 1 and 5. The symmetric axis is x equal to the x coordinate of the vertex. X equal to negative 1. X equal to negative 1. Okay, so it's a vertical axis. Next, form a polynomial function whose real zeros and the degrees are given. A polynomial, we have zeros. Negative 1 multiplicity is 1. 3 multiplicity is 2. And degree is 3. Okay, so the degree is exactly the sum of those two multiplicities. So you will have, we'll only need to find the 1. So it's x minus negative 1. This is one factor with multiplicity 1. So you put 1 here, you can skip that. And x minus 3, multiplicity is 2. And this is your function. And that's it. Don't simplify. Don't do any other steps. And this one you see here, degree 1, degree 2, sum is degree 3. So you do have it. You satisfy all the conditions. Don't do any other step. Okay, so 7. Determine all the asymptotes of the function fx equal to 2x squared plus 3x minus 5 x plus 2. Okay, so it has a denominator. It has a denominator 2. But let's try to see if we can factor this. 2x squared plus 3x minus 5. So you get 2, 1. You have negative 1 and a 5. So you get, it is equal to 2x plus 5. This is a 5, this is negative 2, add a 3. Okay, so 2x plus 5, x minus 1. after factorization it looks like this, and there's nothing you can cancel, so f has a vertical asymptote x equal to -2. Vertical asymptote means the denominator equal to 0. Okay, and it does not have horizontal asymptote because they have different degrees. Okay, the degree of the numerator is greater than the degree of the denominator, but it's exactly by 1, so it has oblique asymptote. Okay, fx has oblique asymptote. How do we find oblique asymptote? We're going to do the long division. So 2x squared plus 3x minus 5 divided by x plus 2. So we put 2x here. We divide the 2x squared by x. We got 2x here. It's 2x squared plus 4x. Do the multiplication. And then you do subtraction. So you get a negative x and minus 5. And then multiply by -1. So negative x minus 2 is a -3. So by this long division, we have fx equal to 2x minus 1 and plus -3 over x plus 2. Okay, so this one, y equal to 2x minus 1 is the oblique asymptote. Oblique asymptote. It has a vertical asymptote, it has an oblique asymptote, and that's it. Okay. Problem 8. Use mathematical induction to prove the statement 1 plus 2 plus 3 plus n is equal to n times n plus 1 over 2. This works for all the positive integers n. So mathematical induction for n is equal to 1. Remember, you're going to prove the statement in Seattle. You're going to prove it, so you cannot assume it is correct. You can only mention left side, right side. The left hand side, when n is a 1, it's just a 1. 1 plus up to 1, so you don't have addition. And right hand side is n is equal to 1, so you get a 1 times 1 plus 1 is 2 divided by 2 is equal to 1. So the left hand side is equal to the right hand side. This comes from your computation. We checked. The statement is checked. Okay, and then assume for n equal to k, the statement is true. Now then for n equal to k plus 1, n is equal to k plus 1. Now still you have to use the left side and right side. The left hand side is 1 plus 2 plus 3 plus n is equal to k plus 1. K plus 1, the previous number is k. The previous integer is k. So 1 plus 2 plus 3 plus k plus 1. And okay, so when n is equal to k, the statement is true. What does it mean? It means the sum from 1 to k is equal to k plus 1 over 2. So this part we use the hypothesis. We assume is correct. So the sum up to k, because we only assume it works for k. Up to k, this is correct. And then plus k plus 1. Okay, so the first term, second term, they both contain factor k plus 1. So we factor out k plus 1. So we have the first one becomes k over 2. The second one becomes 1. And simplified, you get k plus 2 over 2. And you can write it this way. K plus 2 is k plus 1 and plus 1. K plus 2 is k plus 1 and plus 1. Okay? Okay, this is left hand side. The right hand side, when n is equal to k plus 1, is exactly k plus 1 and k plus 1 and plus 1 over 2. So you see it here, the left hand side is equal to the right hand side. So n equal to k plus 1 is checked. Okay, so we check the initial value n is equal to 1. We assume when n is equal to k, then we prove that the statement is correct for k n equal to k plus 1. Then by mathematical induction, the statement is true for all positive integers. For all positive integers. Okay, so that's our problem 8. Problem 8, it always contains 3 steps. Step 1, you check the statement for the initial value. It could be 1, could be 2, could be anything. It depends on the problem. Here, the first positive integer is 1, so we check n equal to 1. And then you assume when n is equal to k, the statement is correct. Then you, based on the statement, what do you mean based on? Based on means you're going to use this statement here. Based on statement when n is equal to k plus 1, you verify that the left hand side is equal to right hand side. So the mathematical induction will guarantee that the proof is correct. Okay. So that's our problem 8. Problem 9. Identify the interval where functions increasing and decreasing on the interval 1, 3. So we have function fx equal to x plus 3 squared plus 4. And the interval is 1, 3. Okay, so first, this is a parabola. Parabola, remember that parabola has 2 types. Either it's open down or it is open up. And open down, open up is controlled by the sign of the leading coefficient. Here, the square has a positive sign. So the graph of fx is open upward. It's this case. For the open upward case, it's going to be decreasing when it's on the left side of symmetric axis, increasing on the right side of symmetric axis. The symmetric axis is x equal to -3. So when you have y equal to x minus h plus k with a, then the symmetric axis is x equal to h. But be careful, here subtraction is always subtraction, is the symmetric axis. So here, this is x plus 3. It's a minus -3. Symmetric axis is x equal to -3. So on the left side is decreasing, right side is increasing. So f is decreasing on -infinity to -3 and increasing on -3 and infinity. This is not part of the solution. I just want to explain it. Okay, and that's the answer for the part 1. And then on the interval 1, 3, on interval 1, 3, you see here this interval 1, 3 is exactly inside this part. So on 0, 1, 3, f is increasing. Okay, 1, 3, this closed interval is totally contained in -3 infinity. It's on the right hand side, so it's increasing. And that's it. That is a problem 9. Okay, and problem 10. Problem 10. List each real zero and its multiplicity and determine whether the graph crosses or touches the x-axis at each x-intercept. Okay, this function is already completely factored, so it's easy to determine the zero. Fx has zeros, 5 with multiplicity 3, -4 with multiplicity 2. F crosses x-axis. When the multiplicity is odd, the graph will cross the x-axis. When the multiplicity is even, the graph will touch the x-axis. So f crosses x-axis at x equal to 5, touches x-axis at x equal to -4. That's it. That is the explanation about the answer for problem 10. Okay, now let's talk about problem 11. That's problem 11. Problem 11, we're going to sketch the graph of the function fx is equal to 3 over x squared minus 4. So you're going to have several steps. Okay, so first the domain. The domain is everything except plus minus 2, right? Plus minus 2 will make the denominator equal to 0. So negative infinity to -2, -2 to +2, and +2 to infinity. You can write it this way. You see here we use parentheses to exclude -2 and 2. Or you can write x is not equal to -2, x is not equal to 2. Either works, either works. And the y-intercept is the value when x is equal to 0. Here 0 is included in the domain, so f0 is a 3 over 0 squared minus 4 is -3 over 4. X-intercept is y equal to 0. No solution. A rational expression is 0 if and only if the numerator is 0. Here, no solution. There's no solution. So it has no x-intercept. It only has a y-intercept. And the asymptote, from here you see here, f has 2 vertical asymptotes. X equal to 2, x equal to -2. 2 vertical asymptote, 2 or -2. And fx has 1 horizontal asymptote. It's because the degree of the numerator is less than the degree of the denominator. When x becomes larger and larger, the limit will be 0. This becomes smaller and smaller, so y equal to 0. So it has 2 vertical asymptotes, 1 horizontal asymptote. Okay, and also you can see that this function is an even function. Fx is even. Even function means it's a symmetric about the y-axis. Okay, it has no x-intercept. It does not touch the x-axis. Okay, okay. Now let's try to sketch it. We have 2, -2, symmetric. Okay, and When x is 0, it's a negative 3 over 4. Negative 3 over 4 is this place. Okay, and you are going to determine that will it go up or go down? At infinite, at vertex asymptote will be either go up or going down. If it go up, it will cross x-axis. Then you will have x-intercept. It's impossible, right? So it will go down like this, symmetric. And then you're going to determine where is the graph of the f on two pieces. Okay, so you're going to test f1, f3. For example, let's try f3. f3 is what? f3 is 3 over 9 minus 4. It's a 3 over 5. It's positive. Some place here. 3 is here. You will have the symmetric part here. And if it go down, you will have x-axis. So it will go up. And horizontal asymptote means it will go here. Symmetrically, you will have this. So this is a graph of a function fx. So you're not going to sketch, I'm not going to give you some crazy graph, but this is a simple graph. Right? Okay, so if you have any questions or doubts about the third partial exam, just let me know. And remember, the third partial exam is closed. Okay? So don't forget that. It's right after the holiday. Okay, thank you.